Hello there, welcome to this introductory lecture. My name is Dr. Sadie Jones and I am a member of staff in physics and astronomy in building 46. We have lots of astronomers who study black holes, like I'm going to talk to you about today, but also things like neutron stars, supernova, which are exploding stars, and things like dark matter and dark energy. The research I'm talking about is what made up my PhD research, and it's all going to be about supermassive black holes, which exists at the centre of every galaxy, but I'll be talking about a specific one that my PhD research was on. So black holes, I'm sure many of you have heard of black holes, but I guess the main problem with black holes is that they are black. Well, in fact, they are not black, they are invisible, and because they have so much gravity, no light can escape the gravity of a black hole, which means that they are invisible and you can't see them in space. So if astronomers can't see them, how do we do research on them? Well, what we do is we look for the radiation around the black hole. So because the black hole itself is so extreme, it has extremely large mass, extremely large gravity, and large magnetic fields, it means that any material that's nearby will be attracted to it and start to spin around the black hole itself. So when material comes towards the black hole, it will gain kinetic energy, it will get hotter, so it will have more thermal energy, and then it will be able to radiate. And that radiation is what we can detect with our telescopes in space. So we learn about black holes from the materials spinning around them. Now, astronomers, as you kind of, the classical astronomer is someone you might imagine using what we call a refracting or reflecting telescope, which is looking in the visible part of the spectrum. And the visible part of the spectrum is the part of the spectrum that our eyes can detect. So visible light is a very important way of understanding the universe, and it is the one that's been done for the longest period of time, right back to the first ever telescopes. But light and radiation comes in lots of other forms. So you can have the radio waves, which is the very kind of low energy but long wavelength radiation, all the way to the gamma rays, which are very high energy and very small wavelength radiation. As an astronomer, we're normally trying to combine different parts of this electromagnetic spectrum to see what kind of radiation is coming from the objects that we're looking at in space. So we might look at it first with visible light by taking a camera, a picture with a camera on the back of a telescope that uses lenses and mirrors. But we could also use an X-ray telescope, for example. Now, this X-ray telescope, Chandra, is actually out in space, outside the atmosphere. And the reason why we need to put telescopes like this outside the atmosphere is because the really high energy X-rays and gamma rays can't actually get through the atmosphere itself. This is really good for us humans because these high energy radiation would be very harmful to us. But if we put the telescope that detects the X-ray outside our atmosphere in space, then it can easily detect any X-rays in the chosen energy range that it's looking at. So this is the kind of image you might see if you go somewhere very dark. So this is taken in the middle of Wales, where I'm from, and this is my friend Hugh and his van, and you can see in the background this kind of hazy light that's forming a stripe across the sky, and this is our Milky Way galaxy. So this is a DSLR camera that he's taken this picture with, and he's left it on a long exposure So you can see lots of stars and gas and dust that you probably wouldn't be able to see with your eyes if you were there on the mountain with him. So you can learn a bit about the Milky Way galaxy just by looking in the visible part of the spectrum. And you can do this locally here in the UK, in Wales. You could analyse the brightness of these stars and maybe even try and figure out where the centre of our Milky Way galaxy was, just from using a kind of standard camera. But for doing other types of astronomy with different wavelengths of light, the what we call the resolving power of the telescope is determined not only by the wavelength of the light you're trying to detect, but also the size of the telescope you're using. Okay, so when I talk about angular resolution, I'm basically talking about, think about pixel sizes. So if you are lucky enough to have a smartphone, the CCD camera in your smartphone that you use to take your selfies has lots of little kind of pixels in it. Now, the smaller the pixel, the more high definition your selfie will look. So if we want to take high definition images of space and have very good, very small number of pixels across the image, then that basically means, well, if you look at this angular resolution formula, all we want to do is make this angular resolution value here, theta, as small as possible to be able to get the best images. So because we're dividing by this d value, which is the diameter of the mirror or diameter of the telescope, then we want that value to be as big as possible. Okay, so because then that will make this number here as small as possible, the angular resolution. So for things like visible light, which is what this telescope here would use because it uses lenses, visible light has a wavelength of 500 nanometers, so very, very small. So to be able to get a very low number for your angular resolution, you actually don't need a mirror which is that big, because this value here of the wavelength is so small. So just keep that in mind. So again, this is another lovely image of the Milky Way. This time this one's taken from a telescope out in space, like Hubble, for example, which doesn't have to worry about the fact that the atmosphere is getting in the way of stars and causing the stars to twinkle and causing errors in the data. Again, so this is now showing you the Milky Way in all the different parts of the electromagnetic spectrum. So optical light is what our eyes see and what I just showed you. So you can, again, see quite a lot of information from this optical. But if you look in all the other different parts of the spectrum, you see there's a lot more going on. There's a lot more detail to our Milky Way galaxy that you wouldn't have known if you hadn't have looked in all these different parts of the spectrum. For example, in the radio waves, when you look at the Milky Way with radio waves, you can see the center is extremely bright, and when you compare that with how the Milky Way looks in gamma ray and X-ray, so the center is still quite bright here in the X-ray and gamma ray, but you have this feature here which is really, really bright, which you couldn't see at all in the optical. And this is actually X-ray and gamma ray radiation left over from a supernova explosion that's happened. Okay, so our Milky Way galaxy has a supermassive black hole at the center of it. This is called Sagittarius A star, and that's just because it's in the, as we see it from the Earth, the supermassive black hole is in the direction of Sagittarius A star, or the Sagittarius constellation. Now, we know there's a supermassive black hole in the Milky Way galaxy because we are able to track the orbits of 6 stars which are orbiting around a central object. Okay, so this is kind of what they look like in space itself. And over time, these blobs move around, and they're moving around a center of mass that is invisible. Okay, so there's nothing there, but the speed, the velocities that these stars are moving at tells us how massive how massive the object is in the middle. And when we do the maths, we come out with a value that is 4 million times more massive than our own sun. So the only thing that can be 4 million times more massive than our own sun and be invisible and be in such a small volume of space is a supermassive black hole. So that's how we know that our supermassive black hole is 4 million times bigger than the sun. So we call the supermassive black hole Sagittarius A star. It isn't a star, it's a black hole, but it's in this region of the Sagittarius constellation, and even in the optical you can see it looks a lot brighter. So there's actually two different types of black holes. There's the black holes I'm talking about today, which are the supermassive black holes at the centres of galaxies. But there are also smaller black holes, which are called stellar mass black holes, which result at the end of massive stars when they die and end their lives. So you have material in space which will stick together, form stars. They will become stars much bigger than our sun, but as they come towards the end of their lives and they run out of their hydrogen, they expand into what's called a red supergiant star. And then at the very end of the life, there will be a pressure and gravitational imbalance between the forces inside the star and the forces outside the star, which will cause it to explode in this extremely bright explosion called a supernova. And depending on how big the star was to start off with, the core of that star will either become a neutron star or a black hole. We call this a stellar mass black hole because it's resulted from a star. And the nice thing about this whole what we call life cycle is that when these supernovae explode, they release, they basically create elements. All the elements in the periodic table up to iron are formed inside the star, and then when it explodes, you get the more complex elements like gold and silver. And basically everything that's in our bodies, everything that exists on the Earth was once formed inside a supernova. And this material is chucked out into space and eventually will stick together under gravity and form new stars, and the whole process starts over again. Okay, but the ones I'm talking about today are supermassive black holes that exist at the center of galaxies. So we think all galaxies have them, but some have what we call active galaxies. So AGN stands for Active Galactic Nuclei, and these are galaxies which are active, which basically just means they have a very bright center, and they may have some jets that come out at a 90-degree angle to the plane of this thing here called the accretion disk. So just to summarize, these two different types of black holes are the supermassive black holes at the centers of galaxies, and these black holes are the orders of millions of times that of the sun, so millions of solar masses. There's also the stellar mass black holes, which are also called binary black holes, and the reason why they're called binary black holes sometimes is because to be able to see these stellar mass black holes, remember black holes are black and invisible, so in order to see them and do our research on them, they're usually with a partner star. And the reason why that is because they rip material off the nearby star, and that material falls into the black hole. And before it does, it forms this thing called an accretion disk, which gives out lots of radiation. And the fact that it is kind of eaten material off the nearby star means that we're able to see it and do our research on it. If it was just a black hole in the middle of the universe with no stars around it, then we would not be able to do our research on it. And these stellar mass black holes have a mass about 10 times the size of the sun, usually. Okay, so my research was on a active galactic nuclei known as NGC 4051. You don't need to worry really much about the this name. Lots of galaxies have kind of weird combinations of letters and numbers. and NGC just stands for National General Catalogue. So because there's so many galaxies, we couldn't give them all nice names like the Milky Way, so we give them numbers. So it looks like this in the optical light, this galaxy that I researched. And if you wanted to find it in the night sky, you would look for the plough. The plough is what you use to find the North Star, and NGC 4051 is just there. So it's quite easy to determine which galaxies are active and which aren't, just by using your normal telescopes, normal cameras, because the active galaxies, like I say, have a brighter center. So you can see more light here in this active galaxy than in this one. So this is an example of an active galaxy. This is a picture in the visible. This one is 12 million light years away, so very far away. And just with our visible image here from a camera, you can see the shape of the galaxy. You can see that it's brighter in the center, which is all nice information, but it isn't until you look at it in other parts of the spectrum with other different types of radiation that has different energies that you will see there's a lot more going on. So the blue here is actually showing you the radiation map for what this galaxy looks like when you use an X-ray telescope, and then the orange bits at the end is actually what you see when you look at it with a radio telescope. So just with the optical, you wouldn't actually know that there was this massive jet, which is then kind of hitting what we call the interstellar medium and creating these big kind of hot spots here in the radio. So this is basically what astronomers do, like myself. We combine the optical, the X-ray and the radio radiation all on the same map, so we can have a better picture of what is going on in these black holes at the centers of galaxies. The current theory is that with active galaxies, the ones that have jets, we know these jets can go for many kind of hundreds of light years into space, but we don't really know how they are ejected and how they're actually kind of attached to the system. So we think it's to do with magnetic field. So just like the Earth has a magnetic field which protects us from kind of nasty things in space, the supermassive black hole at the center of the galaxy will also have a very strong magnetic field. And the jet is basically just lots of particles that, instead of falling into the black hole as they spin around this disk, they are accelerated along the jet instead because of the strong magnetic field. So my research question for my PhD was basically to find out, is there a relationship between the jet, the material in the jet, and the material spinning around the black hole in this accretion disk? So the way I went about doing this was to look at the galaxy with an X-ray telescope in space, which is basically going to be looking primarily at the radiation from the accretion disk, and a radio telescope on the ground, which is basically just going to be looking for any radiation from a jet. And then I will be using the radio dish on the ground, the X-ray telescope in space, looking at the galaxy at exactly the same time and taking data on how bright the galaxy is in X-ray wavelengths and radio wavelengths. So using the Rossi X-ray Timing Explorer, which is in space, pointed it at my galaxy, and this is what we call a light curve. So basically all you need to know is that over time, the brightness of the disk, which was giving off these X-rays, it got brighter and dimmer and then brighter again. Okay, and then before I show you my graph from the radio, the important thing for me to just remind you of is angular resolution. So for radio waves, the problem we have is if we want to get a very small value for the angular resolution, the wavelength of the radio waves is now only 1 meter. Before it was 500 nanometers, which is a very small value, but now it's just 1 meter. So in order to get a very small angular resolution and be able to see features like a jet, which are kind of have a very small angular resolution on the sky, we need to use, or we need to have a telescope with a large D, a large diameter. And the only way we can do this is to do something called interferometry, because if you try to engineer a radio dish that had the diameter needed to give you your chosen angular resolution, it wouldn't be able to hold itself up. It would just collapse. And this has actually happened to radio dishes in the past. People have tried to make them too big and the dish has just collapsed and fallen down. So we use interferometry. So we just connect lots of these radio dishes together using the internet, so high speed fiber optic broadband, to basically make it like as if you're using a telescope, which is the furthest distance between any of the dishes. So this is the telescope I use, the Very Large Array, or VLA, in New Mexico. And basically what this means is when you connect all these different radio dishes together, the diameter of the radio dish that I have is essentially the furthest distance between the dishes. So this, in this case, to get the best resolution, you would move the dishes as far apart as they can go on their radio, on the railway tracks. So you would move the dishes as far apart as they can go on the railway tracks, and this will give you a diameter of 36 kilometers, which is a lot bigger than the diameter of your standard refracting telescope, which was only a few centimeters. Okay, so radio images don't look as exciting as optical images, but all you need to know here really is I'm just drawing a box around the center where the black hole is and taking a measurement of the radio light in that area. And when I've done that, I can produce a graph for the radio brightness over time, and I can compare that with the X-ray brightness over time. So this is what the jet emission in radio, in the radio part of the spectrum was doing. It was also going up and then down and then up. So even by eye, you can see that the X-ray emission from the disk and the radio emission from the jet, they seem to have the same shape. You can see that the X-ray emission from the disk and the radio emission from the jet, they seem to have the same shape, or they seem to have the same brightness over time. So this would actually suggest that perhaps there is, for this galaxy at least, a relationship between the disk and the jet, because you're seeing the same brightness, the same pattern, if you like, over time in both areas. But just to be sure of what's going on, we can actually use something called the VLBI, which means Very Long Baseline Interferometry. And now, instead of just having a 36 kilometer radio dish in New Mexico in America, we're actually connecting radio dishes from across the whole world, which is then giving us a radio telescope the size of the whole Earth. So this means we have really, really good angular resolution. And when we take this image, again, the radio image isn't particularly exciting, but what I got excited about is because these features here, this one in the center is the central black hole, but these two here, the fact that these two kind of features are symmetrical either side of the black hole, and this shape here specifically suggests, I think, that we have got evidence of a jet in this active galaxy that I was doing my PhD on. So that is cool. So basically all of this data that was from my PhD became these triangles you can see here on this graph. So basically we're just plotting the radio brightness and the X-ray brightness with mass of the black hole on a graph. So this is now showing you all the different types of black hole that people have researched with their radio and X-ray telescopes. And you can see the small stellar mass black holes are here. The supermassive black holes are here. And the fact that you can kind of draw a straight line through all these points suggests that there is this relationship between the radio emission from the jet and the X-ray emission from the accretion disk, and that the whole thing scales with mass. Okay, so this is a really important relationship, and lots of people in the department use this relationship. It's called the fundamental plane of black holes. But one mystery that is not explained in this graph is this thing here called intermediate mass black holes. There are little to no evidence, there are no observations as yet of intermediate mass black holes. So these are a bit of a mystery because there is nothing in physics that suggests you can't get black holes which are kind of thousands of size. There is nothing in physics which suggests that you can't get black holes which are kind of 1,000 times the size of the sun. So why don't we see them? Okay, so just to finish, I thought I'd talk about this image here, which is the first direct image of a black hole, which was from 2019. This is an image of an active galactic nuclei called M87, and again, this is a radio image. It doesn't look particularly amazing in terms of resolution, but the fact that there is this hole in the middle that we're able to resolve, this kind of lack of light, as it were, is the first time we've actually been able to directly observe a black hole, the absence of light in an image where we know there is a black hole from our previous observations. So this image was taken with something called the Event Horizon Telescope Array, which is very similar to the VLBI, which I just showed you. But these dishes here are all of the same design. So the data you get and the way you combine them to make your image is a lot more accurate than using lots of different dishes of different designs. And then combining this image here from a radio telescope with the Chandra X-ray telescope in space, you can see that the supermassive black hole and its jet is just doing some very strange things, and the shape is very strange from the jet and the material around the black hole. So again, this is totally new science that we've learned from using radio dishes and X-ray telescopes in combination. And this is Katie Bauman. So she's a researcher at MIT, and she basically came up with the computer program which was able to bring all this information together from the different telescopes and produce the image which was this first direct image of a black hole. So you can see her here looking very excited as the image starts to load on her computer for the first time. Okay, so that's the end of the lecture. I hope you've enjoyed learning a bit more about supermassive black holes, and feel free to ask me any questions you might have about this on Twitter. My handle is @SotonAstrodome. Bye bye.